Hello guys, we're gonna today cover multiple sums and sum manipulations. So if you didn't study your lecture slides, please go back to lecture slides and review them, study them, because it's kind of difficult topic, okay? And if you don't do that, you're gonna be in trouble, guys. Okay, I'm gonna show you a couple of examples how you can approach this kind of problems in this topic. So first of all, let's remember that harmonic series is defined like this, right? Hn is the sum of 1 over k from 1 until n, right? So if you expand this sum, basically what you're going to get is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, so on until 1 over n. So this is what we call harmonic series. Now we're going to use this, okay, to express double sums and triple sums even, right, in terms of harmonic series. And this is even related to more than that. Why? Because in many sorting algorithms, actually, we want to show their efficiency, right? Best case, worst case, and average case efficiencies. And basically, most of the times, they are expressed in terms of log n. And as you know, that this is approximately log n, right? The harmonic series is approximately log n. So that's why it's important to know how to express certain expressions, and especially double sums and triple sums, right, in terms of Hn or in terms of basically log n, right? Okay, let's consider this problem. So express given double sums in terms of Hn or harmonic series. So this is the first one, and we have the second one. If you look at this double sum, you can see that we have this term 1 over k plus 1 and this inside sum, right? So we're going to consider first the inside sum. You see that this index, right, the sum changes by j, right? So j from 1, 2, 3, 4, and so on until k. But in the term itself, under the sum, right, you don't see any j. What does it mean for us? Well, actually, it simplifies the problem. Why? Well, because you don't have the j, there is nothing in this term that changes according to j, right? In that case, we can treat this whole term under the sum as a constant term, right? So as a constant, and if you have a constant, then you're basically adding this constant by itself how many times? Well, in this case, from 1 until k times, right? So basically, if you expand this, you're getting 1 over k plus 1 plus 1 over k plus 1, so on and so on, okay? How many times? K times. And if you're adding something by itself k times, then you can simply write it as this term multiplied by the number of times you are adding it, right? So basically this one, I can write it as, okay, I will keep the outside sum, which is k from 1 until n, and the inside will be simply k multiplied by 1 over k plus 1. Okay? Now I have this term, okay, new term, which I want to transform a little bit as well. Now, how I do transform this is the following way, right? So I want to make the denominator and numerator, right, the same. So to make it the same, what is missing over here is 1, right? So to get 1, all I can do is just add 1 and subtract 1, right? Okay. After that, what we can do is we can now split up this into two ratios, right? This is 1, and then this is the second one into two ratios. So basically what we have is k plus 1 over k plus 1 minus 1 over k plus 1. And the sum changes from 1 until n. Okay, great. So we see that this one and this one cancel out, and this will give me 1. And therefore, I will write it as the sum 1 minus 1 over k plus 1. Okay, as you know, that this sum can be split into two parts, right? Because we have the sum of two terms, 1 and 1 over k plus 1. Well, because minus 1 over k plus 1, right? Okay, so I can write it in two double sums. The sum of 1, right? The sum of 1 n times, right? K from 1 until n. So you're adding 1 itself n times, which as you can guess will be equal to n. And I will have this one over here. Okay, so as I said, adding by itself 1 n times is simply n multiplied by 1, right? Or just simply n. So this is equal to n. And what about this part? Well, we want to make it, okay, in terms of hn, or to make it look like this sum, right? The sum of 1 over k from 1 until n. And how do we make it? Well, if you expand this sum, right, what you can see is that we are starting when k equal to 1, we are starting with 1 over 2, right? If you expand the sum, when k equal to 1, the first term will be 1 over 2. When k equal to 2, the second term is plus 1 over 3. When k equal to 3, it will be 1 over 4, and so on, and so on, and until, right, until when k equal to n, we will have 1 over n plus 1. And remember, guys, that before m 1 over n plus 1, we will have 1 over n, right? So remember that hn, right, is this when it is expanded. So you're starting with 1, right, plus 1 over 2, and so on. You're ending with 1 over n. So we have almost all of the terms, right, except 1. So what I need is 1. And where do I get it? So I'm going to add it and subtract it so that nothing is changing, right? So I'm going to say plus 1 and minus 1. So if I'm adding 1, I should also subtract at the same time so that nothing is changing, right? Because minus 1 plus 1 is 0. And now this term, right, this part is hn, right, by definition. And what is remaining, I will keep, okay, near hn minus 1 and this term. So basically, if I continue with this, we will have the sum, okay. So let's keep it for now like this. So this was equal to n, right? And this one, we transform this one to be minus 1 plus hn plus 1 over n plus 1, right? Remember? And now what I'm going to write is n minus, so remember we have minus outside, and inside I will have minus 1 plus hn plus 1 over n plus 1. Now if I open this up, I will get n plus 1 minus hn and minus 1 over n plus 1. And that's it. So we had this double sum at the beginning, we transformed it and then expressed it in terms of hn. Or we can plug in, right, substitute hn with log n, and you'll get your expression as well, right, in terms of log n. So this is it for this problem. Now let's consider another one. Okay, we have the double sum of 1 over k minus j, and the indexes are given in terms of inequality. So let's consider this problem. The question is again express this double sum in terms of hn, or harmonic series, right? But the indexes are given in terms of inequality. So you should be able to, okay, go back from this kind of, okay, sum or this kind of format to the standard format like this, and from this one to this one. So they are interchangeable, right? And you should be able to do it easily. Now let's expand or see what it means actually, right? So now we can clearly see that k from 1 greater or equal than 1 and less or equal than 1, we can simply write it as k starts with 1 and goes back until n included. Now over here we see that j starts with 1, right? 1 is included, but k is not included, so strictly less than k. So if k is not included, and remember all these terms are integers, right? What is included is the term that is, or element that is before k, right? Before k we have k minus 1. So therefore I'm going to write this as j from 1 until k minus 1. Okay? So you remember that this thing can be written like this, and this thing can be written like this, right? They are the same. It's just different form of expressing sums. Okay, and the term under the sum is, for now, remains the same. Now, we need to look at this carefully. So, many times, students get stuck at this point. So, what to do next? It's kind of not obvious, right, what to do. So, we have k and j, both are indexes, both change, right? And in this case, you have j inside under the sum, and j changes. So the one trick in this case is to try to consider this inner sum and expand it, and to see what happens actually, right? So let's see what happens in this sum. Let's try to expand this. That is, when j equal to 1, j equal to 2, j equal to 3, and so on until j equal to k minus 1, right? And we plug it in all the values of j for j and see what we have for this sum. Okay, so let's see what we get. Now j equal to 1, we're going to get 1 over k minus 1. And j equal to 2, we're going to get 1 over k minus 2. When j equal to 3, you get the logic right, 1 over k minus 3, and so on. And let's say when j equal to k minus 2, so the index before k minus 1, right? It's going to be 1 over k minus 2. And when j equal to k minus 1, what we get is k minus 1, right? So I'm going to write it over here. So this is, okay, you see that these terms are all the same, remain the same, right? So k minus 1, k minus 2, they're decreasing, right? And now if you open this up, you're going to get what? K minus k plus 2. So k and k go away, you have 2. Over here, k minus k go away, and you have plus 1. So basically what is, this sum is basically this, right? 1 over k minus 1 plus 1 over k minus 2, so on until 1 over 2 plus 1. And if you check it out, before 1 over 2, you will have 1 over 3, and before that, you'll have 1 over 4, and so on. And you see that this is actually what? Harmonic series in reverse, right? So this is harmonic series in reverse order. Right? This is harmonic series in reverse order. But what is missing is that the last term in harmonic series is usually 1 over k, right? So I'm going to add 1 over k and subtract 1 over k. So this thing, okay, is now not hn, but obviously since it is in terms of k, this is hk, right? The index will be k. Okay, great. Then I can write this whole thing as, so you see that now if you look at this like this, okay, this simplifies, okay, a lot. So you don't need to struggle right now. You see that immediately when you expand this, this is actually harmonic series in reverse order. Okay, you're just missing one over here. You add one term, subtract it, and express it in terms of again h, right? Harmonic series. Now you already got harmonic series, great. Now what is remaining is, okay, to work with the outer sum. So we have the outside sum from k until k from 1 until n, and inside of it, under the sum, we will have hk, right? And remember that we added 1 over k and we subtracted it. So this subtracted 1 over k remains. So we'll have hk minus 1 over k. Now, as you might guess, next thing we can do is we can split up this into two parts, right? Two sums. So the sum of hk, k from 1 until n, and minus the sum of 1 over k, k from 1 until n. Now, you see that actually this one is immediately hn, right? Your harmonic series in terms of n. And this one, we can keep it like this because we already have harmonic series in it, right? So what I can do is I can write the following: hk, k from 1 until n minus hn. Now we can leave it like this, or we can simplify it even further, right? If you want it, we can write it. Now remember that when k equal to 1, we have h1, k equal to 2, h2, and so on. And when k equal to n, we have hn. So I can split up the last term, write it separately, and keep all the remaining together as a sum. So this will be hk, k from 1 until n minus 1. And over here, I will write separately hn. And I have this minus hn, right? So these two go away. And the only thing that remains is this one. The sum of hk, k from 1 until n minus 1. And if it doesn't look good, well, we can write it even simpler, right? I can write it in terms of inequality. Remember that we can go back from this back to inequality form, right? The index, we can write it in terms of the sum of hk, k. Remember, so over here k starts with 1, so k greater or equal than 1, and until n minus 1. So I can write it less or equal than n minus 1, or I can write it strictly less than n. Like this, right? Like in this example. Remember, if j is strictly less than k, then it means basically that the last index is k minus 1, right? So over here we have the last index is n minus 1, but I can write it in terms of inequality, k is strictly less than n. That means that n not included, but the included index before n is n minus 1. So that's it. So this is the end, and thank you all, guys. I hope this was useful for you, and please do not skip the lectures.